Welcome back everyone to another video in our Fundamentals of Structural Engineering course. In this video, we are going to learn about structural design of steel columns. In the steel design of steel sections for columns and beams, we have two main methods. The first method is using equations, and the second method is using the tables and the graphs which are available in the FE reference book. We are going to learn both methods, even it is very easier to use the tables, but it is also important to understand the equations, so just in case that you needed it in the exam. However, it is still important that you understand properly how to use those tables, because it will save too much time for you, and I'm going to show you how. First, we will start by the method of equations. As we have learned, the steel design for steel columns is mainly governed by the buckling of the column. The steel column will always buckle before it fails due to excessive stresses. That's why we can see here that the formula for the design of compressive strength for steel columns, which is phi Pn, where phi equals 0.9 for steel elements, we can see that Pn equals F critical multiplied by Ag. This is where Ag is the area gross of the steel section, and FCR is the F critical, which is the F you are going to use, or the strength you are going to use to limit or to prevent any buckling for this steel column. FCR, or the F critical, has two cases here. In the first case, LC over R is less than 4.71 root E over F yield. In this case, the F critical is going to be calculated by this equation, which is 0.658 power F yield over Fe multiplied by F yield. And in the second case, if LC over R, which is the slenderness ratio, is more than 4.71 root E over F yield, in this case, F critical will equal 0.877 Fe, while Fe is the elastic buckling stress, and it is calculated by this equation, which is pi squared E over KL over R square. This means that in order to calculate the strength of the steel column, you need to obtain the F critical, and in order to obtain the F critical, you need to know first the slenderness ratio, so you understand in which equation you are going to use, and in order to use the equation, you need to get the Fe, which is the elastic buckling stress, which you get it from this equation. So this is the process of solving any column problem, any steel column problem in the exam. This is using the equations method. Now I'm going to show you how to use the tables method, which you are going to see that it is way simpler, of course, and it will save too much time for you. We have those two main tables. I'm going to show you to now in the FE reference book, which are table number 4.1 and table number 4.14. Table 4.14 using the slenderness ratio of any steel element, which is KL over I, and in case of F yield equals 50 KSI and phi equals 0.9, which is almost always the values which will be given to you. Always we use the phi as 0.9, and F yield, it's almost 99% of the time it is going to be given to you as 50 KSI. If it is given as different value, of course, in this case you will not be able to use this table. But as I'm saying, most of the time it is F yield equals 50 KSI. So in this case, you are going to refer here to this KL over R. You are going to use to whatever value of KL over R which you have. For example, here 22. You can see here opposite to it, this is the value of the phi FCR, which will be 43.4, or whatever value you will get here depending on the KL over R. So without even calculating the Fe, without calculating the equation for the F critical, all of that, just using the KL over R, you will go here to the specific value, and opposite to it you will find the value which you need, which is phi FCR. Here in the table 4.1, this is even a more important table, or it makes your life even easier. Here we have selected sections which are W14, W12, W10, and for each one we have different weights for the sections. So those are different sections, W14 for example 74, 68, 61, whatever. And also using the slenderness ratio of the section, here you are going to get directly the phi Pn, which means that it is just the FCR multiplied by the area gross of the section. So here you will get directly the load, which is the maximum safe load to apply on this section. This is of course considering that F yield equals 50 KSI and phi equals 0.9. So here we have those two tables, 4.14 and 4.1. This is for the available critical stress and this is for the available strength. This is the title of each table. This table, it gives you a relation between the column's slenderness and the allowable critical stress. And this is this table gives you the maximum allowable axial force for each column based on its slenderness. You need, for each of those tables, you need to have the unbraced length. You need to have the K, which is the effective length parameter, and which we discussed in our first introductory video. And you need to have R, which is the radius of gyration. And this you get it from the table of the properties of the steel section. And from all of these values, you get the phi FCR. And for the second table, you need almost the same data, except you need also the section name, and you will get the phi Pn, which is the axial force for the column. So now, let's have an example on this. Here we have a steel compression member, which is a steel, let's say, column, has a yield strength of 50 kips per inch square, 50 KSI, and a controlling slenderness ratio of 31.8. The critical column design stress is most nearly. So here we want to calculate the critical column design stress, which is phi FCR, and we have here F yield, and we have the slenderness ratio, which is 31.8. So let's calculate first our limit, which is 4.71 root E over F yield, which equals 4.71 root 29,000 over 50. This is the youngest modulus of the steel in general, unless it is given as different value, but otherwise this is the default value for the steel. This is going to equal 113.4. This is almost a fixed value because, as you can see, E is a fixed value and F yield most of the time it is fixed value. So for any F yield of 50 KSI F yield, you will find that your limit is 113.4. And you know that slenderness ratio here you have is 31.8, which means that the slenderness ratio, which is 31.8, is less than our limit here, which is 4.71 root E over F yield. This means that FCR is going to be governed by this equation, which is 0.658 power F yield over FE all multiplied by F yield. So now we need to calculate FE, which equals pi square E over KL over R all squared. So this is the equation for the FE. Let's just substitute now. So it is going to be 3.14 squared multiplied by 29,000 all over 31.8 squared, because this term here is the slenderness ratio. So FE is going to equal 283 kips per inch square. So now you have FE. This means that F critical is going to equal 0.658 power F yield over FE all multiplied by F yield. This means that F critical equals 0.658 power 50 over 283, all of this multiplied by 50, which is going to be 46.4 KSI or kips per inch square. But you need to take care that this is FCR. We still need to calculate the phi FCR, which is going to equal 0.9. This is the fixed value for the steel. This is the strength reduction factor multiplied by 46.4, which is going to equal approximately 42 KSI. So this is the answer here, which is 42 KSI. Now I'm going to show you how you could have solved this problem using the tables, and you will see how much time you are going to save. Here we have this table, 4.14. We have F yield equals 50 KSI, which is given in our problem, and we have phi equals 0.9, which is the default value for the steel members. We know that KL over R equals 31.8, which is going to be here between 31 and 32 and approximately 32. In front of it here, you will see this is the phi FCR per KSI. So if it is approximately 32, you will get that the design strength or the phi FCR equals 41.8, which is approximately 42. So you can see that it is literally in just few seconds you solved this problem without even using a single equation. That's why I told you it is very important to understand how to use the tables in the exam, because it is going to save you a lot of time. Try to solve multiple problems using both the equations and the tables, so you will understand the difference, and also you will get better practice in using the tables. So this is it for our video today. See you in our next video. Thank you.